till the previous video, we saw these two quantities, L epsilon p and L bar p, where the first was the minimum number of bits required to represent a random variable with distribution p. So x, we assumed there was a random variable x with distribution p, and we wanted to compress these symbols, generate this x, the source x, and L epsilon p is the minimum number of bits required so that you are correct with probability at least 1 minus epsilon. And L bar p was the average number of bits required when no error is allowed. So you want a one-to-one mapping, but you count average number of bits. And what we saw towards the end of the previous video was that these two quantities are roughly the same. They differ only in terms of this parameter epsilon. Okay, this parameter epsilon. And that's the only way in which these two quantities differ. Otherwise, they're roughly the same. And this parameter epsilon is nothing very fundamental to a formulation. It's an accuracy parameter. It's something like 0.99, which we can agree on. And so we don't worry about the dependence on this epsilon at this point because we were looking for a conceptual definition of or a measure of uncertainty. And both these are good candidates. And now we saw that these two are similar quantities, so we can focus on any one of them. We'll focus on this guy, L epsilon p, the minimum number of bits required to recover a random variable, the minimum number of bits required to express a random variable, so that so that you can correctly recover it with accuracy at least with accuracy in probability at least 1 minus epsilon, right? And we did characterize this L epsilon p exactly. We showed that this L epsilon p is exactly equal to this log to the base 2 of n epsilon p, where n epsilon p was the least L, such that when you take the L largest probability symbols, then their probability adds to 1 minus epsilon. So you will just, the scheme which attains this L epsilon p is exactly that. It just retains this L largest probability symbols, such that the probability of those symbols together exceeds 1 minus epsilon. So we had an exact expression for this L epsilon p, but it may not look very useful in the sense that it's a little bit of a complicated formula and it still not gives us enough feeling about how do we measure uncertainty. One thing we realized was that somehow this compression was related to uncertainty. That was actually our thesis. We believed that upfront. And what we realize is that a good compression scheme does the following. It assigns shorter length sequences to symbols with large probability. Okay. However, this expression is still not very useful because for beginning it has an epsilon inbuilt into it. There's some dependence on epsilon. And epsilon is some accuracy parameter. It's not a fundamental quantity towards expressing towards measuring uncertainty in a random variable. So it's just something that we came up with to have a mathematical formulation. So now what we'll do today, we'll find an approximate upper bound for L epsilon p. So an approximate upper bound for L epsilon p that is not as accurate as the previous one, as this formula we just saw, but it brings out the more fundamental notion of uncertainty. It will bring out a new feature of p that measures its uncertainty. Okay. So how do we come up with that? So here is an alternative scheme. So remember our previous scheme was taking L largest probability symbols and keeping them. And this L was chosen so that the collective probability of this symbol exceeds 1 minus epsilon. Note that if you take all the symbols, the probability will become 1. And if you take no symbol, the probability is 0. So as you add symbol one at a time, at some point you will exceed 1 minus epsilon. And that's when you stop. And those are the symbols you retain. Okay, because we are allowed to ignore symbols with probability less than epsilon. Okay. Alternatively, instead of looking for this L largest probability symbols, what we can do is we can retain symbols which are more likely than a threshold, which are more likely to occur than a threshold. So in particular, we consider this set A lambda, where this threshold of acceptable symbols is said to be 2 to the power minus lambda. It's the set of all those symbols x whose probability px exceeds 2 to the power minus lambda. So they have a reasonable probability. We just retain those symbols. So instead of L largest, we'll retain these symbols. You can take a log and re-express this as minus log px less than equal to lambda. So there's another view of this set. You can think of this minus log px, a quantity which will come up again and again, as a measure of rarity of a symbol. Okay. A symbol is very rare if minus log px is large. Okay, and we retain those symbols which are not too rare. That's what the set A lambda is. Okay, so we can define the set A lambda and retain symbols in this A lambda. Here is a very simple exercise. This one here. I'll urge you to take a pause and try to solve it, but I'll solve it right away. We have to show that the cardinality of A lambda is less than or equal to lambda. Can you pause and try to show this? Okay, now that you have tried to work on this exercise, I'll just prove it in one line here. It's a very simple exercise, but very basic one, very interesting one. So if you look at all the symbols x in A lambda and add their probability, that probability cannot exceed 1 because the sum of probabilities of the entire set is 1. Right? That probability cannot exceed 1. But the probability of each symbol here was at least 2 to the power minus lambda. Remember, that was our definition for A lambda, is a symbols with probability greater than 2 to the power minus lambda. So you substitute that lower bound on each of these quantities. So this sum here, each term is greater than 2 to the power minus lambda. And how many terms are there? Well, the cardinality of A lambda. Therefore, the cardinality of such set cannot be more than 2 to the power lambda. Oh, this exercise is a log missing here, sorry. Yeah, sorry about that. So log of A lambda is less than or equal to lambda. Okay. So there are not more than 2 to the power lambda sequences in A lambda. That's what this exercise claims. So let me remove this proof. Okay, fine. So with this observation, here is a simple theorem, simple to state, but very interesting. It gives a nice handle over this L epsilon p. For any lambda, if you consider the set A lambda and store the sequences in that set A lambda, suppose that A lambda has probability greater than 1 minus epsilon. Okay. We already saw that there are no more than 2 to the power lambda sequences in A lambda, so we can store all the sequences in A lambda using less than or equal to lambda bits. So if its probability is greater than 1 minus epsilon, then A lambda constitutes, storing all the elements in A lambda constitutes a valid scheme for L epsilon p, and therefore L epsilon p, which is the minimum over all such schemes, minimum length over all such schemes, must be less than or equal to lambda. Okay, therefore L epsilon p is less than or equal to lambda. Okay, so for any lambda, how do we find such a lambda which satisfies this? That's a different problem. But suppose you found it, then we have an upper bound for P epsilon, L epsilon p. There's a way to say this bound in words. What it says is a large probability, a 1 minus epsilon probability upper bound on the random variable. So you can think of this minus log px as a random variable. This random variable is very fundamental for this course. Just remember, we call this a measure of rarity, right? So this minus log px, it's a random variable because x is random. This is a measure of rarity of an element. Any large probability upper bound on this is actually an upper bound on L epsilon p. Any upper bound on this which holds with probability greater than 1 minus epsilon, like this one here, is an upper bound for L epsilon p. Okay. So now, can we give a more concrete upper bound? For that we need a large probability upper bound on this random variable set. Now, what is a good estimate for large probability upper bounds on random variable? That's where we just saw Markov inequality, right? So Markov inequality gives a nice upper bound like that. It tells us that expected value of a random variable is such an upper bound. The expected value of random variable by epsilon, for instance, is a large probability upper bound on the random variable. So let's try that upper bound. So a theorem says that, by a theorem, the random variable we are looking at is minus log px. So its expected value of minus log px serves as a large probability upper bound, minus log px by epsilon. So this quantity will serve as an upper bound for this length, and in fact this quantity is the fundamental measure of uncertainty we were looking for. So we can expand this. You can see that this expected value is sum over x px log 1 by px, and it has a name. It is the Shannon entropy. Okay, so this is the first important quantity we see in this course. It's denoted by h of p. Shannon entropy of a random variable p, of a random variable with PMF p is denoted by h of p. So h of p is summation over x px log 1 by px. Remember, this log 1 by px is the rarity of a symbol. It's sometimes also called the entropy random variable or entropy density, and its expected value is the entropy. So that and what we have seen is that L epsilon p is less than equal to entropy by epsilon. That's what we have seen. All right. So great. So we have discovered Shannon entropy as a measure of uncertainty. We have given a formal theorem which says, first we said that, okay, we'll measure uncertainty by the minimum number of bits required to represent that random variable. Then this quantity L epsilon p is the answer to that problem. But we could get an exact expression for this L epsilon p, but that was not very nice because it's difficult to interpret it. So we look for approximations to this. We haven't commented how good these approximations are, but it will turn out these are actually pretty good approximation. We will show that this quantity is actually approximately equal to the Shannon entropy itself if we ignore the dependence on epsilon. And therefore Shannon entropy emerges as a measure of uncertainty and also as a measure of as an answer to this the fundamental limit of compression L epsilon p. And I would request you to, after this lecture, to look at this quantity, play around with it and try to remember it. So here are some very simple exercises to help us understand what the Shannon entropy is about. Of course, we'll spend a lot of time in reviewing properties of Shannon entropy, but here is a small warm-up exercise. Okay, so you can do it yourself. You can look at it and take a pause the video here and try it yourself. I'll quickly solve it now. Okay. So this first exercise, compute Shannon entropy of P. Okay, for this. So this distribution here is a uniform distribution on 1024 elements. So one thing which we'll see later is that h of P for P which is uniform on any set. Okay, let's say a set of cardinality K. So this is the set 1 to K. Any P which is uniform here, its Shannon entropy is just log of K. You can show that. So this is log of 1024, which is 10. So this entropy is 10. Okay, next one. What is the Shannon entropy of this guy? So what is this sequence? It has one element with very large probability, half, one element with smaller probability, 1/4, and remaining the same. So which one do you think is higher entropy, this one or this one? So since this is completely random, so for us the answer here is 10. This one is completely random. This should have higher uncertainty. Shannon entropy for this is 10. So if this is a reasonable measure of uncertainty, the entropy for this one must be smaller, at least smaller than this. Okay, so let's compute. This is sorry. This is A. This is B. So with probability half, it's log to the base 2 of half, 1 by half, which is 2. So that's 1. Probability 4, 1/4, it's 2 plus probability. What is this probability? So all these are 1024, 1024. How many are remaining? So you have 3 by 4 symbols. Okay. So 3 by 4, what's the probability of these symbols? It's 1/4. Each of the symbols has probability 1/4 into the total probability is 1/4 of these symbols, and each symbol has probability log of 1 by 1024, which is 10. So 10, right? So the total comes out to be 2 here. So 2 plus 2, 4, 4 plus 10, 14, 14 by 4. Okay. So which is less than 10. So this has smaller entropy than 10. Okay. It has 7 by 2. Okay. So that's 3.5. How about this guy? Now, it was easy to compare these two, but what a measure like this will do is also allow you to compare this with this. Which of these two have higher entropy? So you can compute this entropy and check and let me know. Once again, what I mean by this 1024 throughout here is that all the other symbols have probability 1024. How many symbols? Well, it's 1/4 probability remaining, and 1 by 4 by 1024. That's the number of symbols remaining. Okay. Second exercise is also very revealing. It's very interesting. It asks you to plot entropy of Bernoulli P. So Bernoulli P just has two probabilities. plus 1 minus p log 1 by 1 minus p. So you can plot this function. Okay, so you will see that at p equal to 0 it is 0, and at p equal to 1 it is again 0. At p equal to half it peaks to its value, and that's 1, and it's what is called a concave function, which attains its maximum at p equal to half, and it's symmetric around half, although my drawing is really bad, it doesn't look symmetric, but it is symmetric about half. Okay, right, so good. So this was a very important lecture, and it sort of concludes our discussion in this week till now. We have discovered this measure of uncertainty as Shannon entropy. In many books, this notion is introduced upfront without any operational meaning. Instead of that, what I did in this lecture series is I tried to motivate a more philosophical problem of measuring uncertainty, and slowly discovered Shannon entropy as an answer to that problem. Okay, and this will be our approach throughout this course. We will not introduce many of the quantities up front. We will slowly motivate them through operational problems and try to discover them. And later on, we'll revisit them and study their properties. Okay, so see you in the next video.